This is lesson 5.4, part 2. We're looking at the learning target of I can use sum and difference identities to solve trigonometric equations. So that's the learning target that this part 2, is focused on. Cofunction. A cofunction we already defined cofunction identities back in lesson 5.1 and 5.2, and basically the sine of x, if you recall, equals cosine of 90 degrees minus x, or pi over 2 minus x. And the same thing is true for cosine of x. It's pi over 2 minus x inside of sine. And then also for cotangent, tangent and cotangent, we have the same thing. So verify each cofunction identity using a difference identity. So here we have, right, we have this equation. They want us to show that this and this are equal, not using that identity, but using a different identity. And so, since in this lesson we learned how to do sum or difference identities, we can actually do this because we have a difference identity right here. So we have cosine of pi over 2 times cosine of x plus sine of pi over 2 times sine of x. And we're supposed to show that that equals sine of x. That's what we're trying to do, is prove that right there. All right. So cosine of pi over 2 is 0. So this becomes 0 times cosine of x, which is 0. And sine of pi over 2 is 1 times sine of x is sine of x. So we have sine of x equals sine of x using that identity. Try this for letter B. Pause the video, try this for letter B. Cosecant identity, same idea. We have cosecant of pi over 2 well, we don't have one and a sum or difference for that, but we do know that cosecant is the reciprocal, I'm going to need more space than this, is the reciprocal identity of sine. So I can rewrite this as 1 over sine of pi over 2 minus theta. And then I can expand the sine of pi over 2 minus theta using the difference of sums. Or, sorry, the difference of angles for sine difference identity. So I have sine of pi over 2 cosine theta minus sine of theta cosine pi over 2. Well, sine of pi over 2 we already know is 1, and cosine of pi over 2 is 0, so I have 1 times cosine theta minus, that's going to be sine theta times 0, which is 0. So right now I have 1 over cosine theta, because this was all in the denominator. And that is equal to secant theta. So we should be able to use the sum and difference identities to prove some of these cofunction identities. We have something else called the reduction identity. All right, formal definition, reduction identity. When a sum or difference identity can be used to rewrite the expression with one of the angles being pi over 2, like some of the problems that we just did, especially with cosine and sine, it makes one of them 0, cosine makes one of them sine 1. It reduces the complexity of the expression. Then it's called a reduction identity. So let's take a look at how we can do that. with this. And when it says with one of them being pi over 2, or a multiple, I should say, a multiple of pi over 2 are quadrantal angles, if you will. So it doesn't have to be pi over 2, it could be a multiple. So if it's any of our quadrantal angles, if you can rewrite any expression, sum or difference, and using quadrantal angles, it will reduce it, make it easier. So here we go, we have tangent of x. We're supposed to verify these reduction identities. Well, for tangent, we're going to use the difference of tangents, which is tangent of x minus tangent of 360 degrees all over 1 plus tangent of x times tangent of 360. Well, tangent of 360 degrees is 0 over 1, which is 0. So this gives me tangent of x minus 0, which is just tangent of x. And on the bottom, I have 1 plus tangent of x times 0, since tangent of 360 is 0. So that's gone and that's gone, leaving us with tangent of x over 1. It greatly reduced the complexity of the expression. So this is a reduction identity. Letter B, same idea. It's a multiple, or it's one of our quadrantal angles, or if we could make it be written as one of our quadrantal angles, we could do the same thing. Sine of 3 pi over 2 cosine theta plus sine of theta cosine 3 pi over 2. Well, 3 pi over 2, the sine is negative 1 and the cosine is 0. So I have negative 1 times cosine of theta plus sine of theta times 0. So this expression goes away completely, and I have the opposite of cosine of theta, which is what I was supposed to use to prove this reduction identity. Find the solutions to each equation on the interval from and including 0 up to 2 pi. So we're now going to use our identities to solve trigonometric equations. Yesterday, all we did was expand them. I would get familiar with using the trigonometric identities, the sum and difference identities, and how to simplify expressions with them and write exact values. But now we're actually solving equations using them. So for letter A, I have sine of this. So I'm going to rewrite this as sine of x cosine of pi over 4 plus sine of pi over 4 times cosine of x. And then I've got to be careful because I have to do, I'm just going to write across the whole screen and erase it. It's just going to be easier for me. Minus the entire thing. So this is sine of x cosine of pi over 4 minus sine of pi over 4 cosine of x. So I have to simplify what's in parentheses, and then I have to distribute the negative. If you choose to, you can distribute the negative first. I'm going to simplify what's in parentheses first. We know that both cosine of pi over 4 and sine of pi over 4 are both square roots of 2 over 2. So what I have is sine of square roots of 2 over 2 sine x plus square roots of 2 over 2 cosine x. And we'll distribute this negative in a minute. And here we have square roots of 2 over 2 sine x minus square roots of 2 over 2 cosine x. And now I'm going to distribute that negative, making this negative square roots of 2 over 2 sine x, and this positive square roots of 2 over 2 cosine of x. I feel like I missed something. Nope, that's right so far. So now I have, says it's supposed to be 0. Sine x plus square roots of 2 over 2 cosine x. And so these definitely cancel out because you've got one positive, one negative. Those are not canceling out. That's going to be square roots of 2 cosine x And I need to look at that and figure out what I did wrong. So just give me 1 second. I don't think it's wrong. Okay, nothing's wrong. I did everything right. I'm trying to solve this. I was in the mindset of what we were doing up here where we were trying to prove a reduction identity. And so because we were trying to verify an identity like what we did in section 1 or 5.1 and 5.2, I was locking the right side at 0, and it's not equal to 0. It shouldn't be. So when I add these, I have a half here, right? This is square root of 2 cosine x, or half of it, and half of it here. So all in all, I have 1 whole square root of 2 cosine x, and that's equal to 0. So far, I'm not verifying an identity here. I just had said we were solving. So we are solving this equation. When is this equal to 0? Well, I can divide by square root of 2. I can't divide by a trig function or divide by anything that has x in it, but I can divide by square root of 2. So in reality, I'm looking for when is cosine of x equal to 0. So when is cosine x equal to 0, the answers are pi over 2 and 3 pi over 2. So we have to pay attention to what we're doing, because I thought I was wrong because I thought I was proving an identity, but we did it right. All right, so when we go to do the next problem, which I'm going to erase this in a second, we're going to do the same thing. We're going to expand the left side, we're going to expand the right side, and some things may or may not cancel or be eliminated. It is a quadrantal angle, pi is, so that should help reduce the identity, or reduce the expression. So we're going to clear this, clear the ink. And so for this side, I have cosine of x, so it's going to be cosine x cosine pi minus sine x sine pi. And on the right side of our equation, I want to make sure I put a big fat equal sign in there so don't miss anything. We're going to have sine x cosine pi minus sine pi cosine x. Well, at pi, sine is 0 and cosine is 1. So this becomes 1 times cosine, so that's just going to be cosine x. This becomes 0 times sine of x, or times negative sine of x, which is just 0. Still have our equal sign. This becomes 1 times sine of x. So we have sine of x. And then this sine of that becomes 0, so minus, no, yes, 0 times cosine x, so that becomes 0. So now I have cosine x equals sine x, which is not a true identity except for a specific value of x. So some of us already know, I think I know what the answers are, and there will probably be 4 of them, but maybe not, because we might need to check for extraneous solutions. Should still, no, they won't always be equal. All right, because I can't change them using an identity right now, I'm going to square both sides. But remember, when we square both sides, we've taken something that, although sine and cosine aren't really linear, thinking about it in terms of x, x was linear, and now we've squared it. So we've gone from one solution to introducing more than one solution. So not all of the solutions will be answers. We may have extraneous solutions. So we have to check for that. So let's take a look. When I do this, I'm going to choose, I like to keep it as sine. You can keep it as cosine if you want. I'm going to make this 1 minus sine squared of x using the Pythagorean identity. I'm going to move everything to one side by adding sine of x, sine squared of x, and subtracting 1. So what I end up with is 0 equals 2 sine squared of x minus 1. Well, I don't need to factor this. I can't even factor it because of the 2. I'm going to add the 1, and I'm going to divide by 2, and I have sine squared x equals 1/2. I'm going to do plus or minus. Don't forget the plus or minus. For some reason, some of the pre-calc students have been forgetting that. Right. So now I have sine of x equals plus or minus square root of 2 over 2. Well, that's easy. So x, sine of x equals positive square root of 2 over 2. or sine of x equals negative square root of 2 over 2. Now we're going to take a look at what answers we get with this. Some of you already know from previous homework assignments that you've done where you had a similar equation or the exact same one. Sine of x is square root of 2 over 2 at pi over 4, and also positive square root of 2 over 2 at 3 pi over 4. So we have pi over 4 and 3 pi over 4, giving us our two answers from quadrant 1. And from quadrant 2, our two positive answers for sine. Our negative answers for sine being square root of 2 over 2 is going to be 5 pi over 4 and 7 pi over 4. So in quadrant 3, we have 5 pi over 4. And in quadrant 4, we have 7 pi over 4. So there are our answers for what we just solved after we squared. But that does not mean that cosine of x equals, where I can go back to what it was before I squared it, or I could go back to the original equation. I'm going to go back to where it was to make sense of it, because you've solved problems like this before. Cosine and sine are equal. That is not true in every quadrant. It is true in quadrant 1, because all trig functions are positive. So quadrant 1 is good. That checks out. Cosine of pi over 4 and sine of pi over 4 are the same value, square root of 2 over 2. And in quadrant 2, that's not the case. They're actually opposites. So quadrant 2 is one of our extraneous solutions. And then in quadrant 3, both sine and cosine are negative. So quadrant 3 works. Quadrant 4, sine is negative, but cosine is positive. So that is also an extraneous solution. So because we squared both sides, we had to plug them back in and check. Now that would also have worked if you'd gone back up to the original equation and plugged that in. It's a little more work because you have to do the pi over 4 plus pi or the pi over 4 minus pi. And then you may have to find coterminal angles within the unit circle to solve that. But the same idea applies. If I go back to what I had before I squared, that equation should still be true. When I square both sides, I've introduced additional solutions, and we have to check for extraneous. So here's how we solve equations using the sum and difference identities. In class, you'll be doing some practice with solving equations like these.